Welcome, everybody, to the Imaging Wire show. My name is Jake Fishman. I produce the Imaging Wire, and I'm super happy to have Jason Knapp with me. Jason leads AI development, just about everything else on the technology side at Riverain Technologies. And he's also one of the really good guys of our industry and a really smart guy. I'm looking forward to sharing all those good guy and smart guy tidbits with all of you. And so welcome, Jason, first of all.
Thanks, Jake. Thanks for having me.
Really good to have you with me, bud. So we're just going to jump right into it. And the first question is kind of a heavy hitting one. Is Ohio State football the best football program in the country or in the world?
That's a softball. I mean, clearly it's the best program in the world. So, the Midwesterners, we like our football. So yes, big Buckeye fan.
Okay. All right. So then on to the easy stuff. So actually, it's interesting because I end up kind of coming across a lot of folks who are AI experts or AI developers, and you don't necessarily seem like the typical one, right? You're in the Midwest, like you said, and right. You got like a different type of accent than maybe the other ones. And I'm curious, how did you end up on this path?
I was actually a math and electrical engineering major, and going through sort of trying to figure out whether I wanted to be just a pure engineer or a mathematician. And around my junior year, I was actually leaning more toward the mathematics side of things in terms of, doing a PhD. And I met a fellow student who was doing an internship at a local company called Qualia Computing. And so he was pretty adamant that I should come check it out. I did. This company, Qualia Computing, was a mammography CAD company. So it was a sort of a startup that was started by a bunch of academics at a local university, one of which was Steve Rogers, who was really a big neural nets guy back from the 90s. Maybe not a household name like, say, Jeff Hinton, but did quite a bit of original work with the students. And so Steve had sort of personal motivations to do this, to take the stuff that he had worked on in, say, military applications and see if he could apply it to medicine. So anyway, I find myself in here as an intern. So I went in, I loved it. And it sort of changed the course of my life. I got introduced to, it wasn't really called machine learning then, it was called pattern recognition. But it was, mainly the same topic, just it had a different sort of historical past, so therefore a different name. And so, that sort of radically altered my plan. So, at that point, I'm still an undergrad. So, but a couple of semesters later, I took the course in machine learning that was there by an individual who, at the time, I actually think was one of the best graduate level machine learning courses in the country. A guy named Ricardo Gutierrez and Sonia. Who would go on to be my master's thesis advisor. At any rate, I fell in love with the topic right away. The application area of trying to use your problem-solving skills to help medicine, that was very attractive. And so, so there was really no looking back after that. Went from an internship into a full-time position. Went from junior engineer to senior engineer, research scientist, and really. Kind of an interesting point in time. It was during the time where mammography was going from digitized film to FFDM. So it was sort of an interesting moment to be involved because you got to see quite a bit of things that where the technology had its limitations. I mean, obviously, as you are no doubt aware that, and your viewers are as well, that the CAD sort of has this sort of tarnished reputation. Like any application of perception from, say, circa 2000, speech recognition, these things were not that good because the sort of ambient technology and understanding of how to work these problems was not there. I learned a ton. It was a wonderful experience, and spent many years there before moving over to Riverain. So that's a long story, but that's how it happened. So. Yeah.
It's a great story and really impressive to have that front row seat. So you mentioned kind of some of the learning moments going from that early technology to where we are today. Are there certain things you learned along the way that really seem to be particularly important now?
Oh yeah, tons. I mean, really nothing new under the sun. I mean, CAD and AI are just acronyms, right? I mean, it's really applied machine learning, so building predictive models. And so while the level of performance has certainly improved with today's models, I mean, the core issues haven't changed at all. Okay, so maybe one example of things that I saw the old CAD system sort of work through, kind of go through was you had these legacy CAD engines that were trained on digitized films. He had these big repositories of data sets where these models were built on top of, right? And so when they would then take those models and apply them to the newer FFDM sensors, even though they were cleaner data and so forth, the models didn't work. And this was during the hand engineered feature days, right? So the reason why the models didn't work was because the features that were these measurements that were being used to do automatic decision making, they were themselves sensitive to the underlying changes in acquisition. That problem still exists today. I mean, if you look at the literature, you'll see this goes under different names, but domain adaptation is sort of the research area that tries to account for changes in the distribution. In other words, I have some images that were collected on this type of device, and now I have another set of images, and the question is, will a model work across those? So that was sort of very sort of instructive. A colleague of mine at the time, who's now Riverain CEO, Steve Worrell, he has a background like in optics physics, so he kind of looked at that problem and sort of looked at it as from like an inverse imaging point of view, which I thought was really pretty clever. And so in mammography, you had maybe 4 or 5 vendors, okay, at most at the time. Maybe that's still true. I honestly don't know. But so you could develop a sort of point-to-point type of adaptation solution for these changes in devices. And so so when it came to chest from mammography, I mean, there's hundreds of chest sort of exams, and unlike in mammography, you don't have access to the raw data, so you don't have, it's not just simple imaging physics where you have certain statistical noise or whatever, just all this sort of post processing and so forth. So that actually really presented a challenge. That was something I sort of, one of the sort of core pieces I had to work on later at Riverain. But anyway, that was definitely influential. But when I actually went to work at Qualia, you would think because of Steve Rogers' background that neural nets would have been really pervasive in all the applications, but they were not. They were actually had a stigma about them. Most of the engineers that worked there were from the sort of statistical pattern recognition, type work, and I got involved in different areas. And so one of the things I worked on lots of machine learning stuff. So neural nets was one. Actually, was one of the things I did was to sort of show that you can actually build neural nets and really make them work really well, but it takes more effort. And I think ultimately that was part of the problem, that they weren't as easy to use from the point of view of making sure they behave well as other models at the time. And other things were sort of in fashion at the time, so kernel methods, support vector machines, these type of things. So, but at any rate, I got exposed to lots of neural net stuff, and so I've been using neural nets for 20 years now, so that's definitely something. It's not so much that I was sort of inspired by the brain. It's just that they were good. If you craft them, correctly, you can build really good models. So that all happened in that sort of span of say 4 or 5 years.
You take all those learnings and here you are for the last bunch of years at Riverain. How have you kind of applied what you've accumulated up until this point to create the Riverain product line?
So when I came to Riverain, the sort of initial ambition there was to sort of do sort of CAD for lung nodules and chest X-rays as is done for mammography. And in retrospect, that was not a great idea. You can sort of appreciate the analogy, but it's not, certainly given the technology at the time, it was not necessarily the best approach, the best sort of way to do things. But nevertheless, my first couple of years here was spent building a sort of CAD for chest X-ray. And if I was an academic, I got quite a few publications, but ultimately, the thing that we built was, it wasn't good enough for clinical use, even though by comparison to mammography, it was much better performance-wise. But again, we didn't have deep learning, so it was neural net based, but it wasn't, the models that can give you these ultra high specificity, which was really the problem. So, but during this period of time, at Riverain, there was some work that came out that looked to use machine learning to do bone suppression. So this work came out of Chicago Kunio Doi and Kenji Suzuki. Another group led by Bram von Ginnigan also did similar work around the same time. So one of the things I did was to sort of say, okay, well, let's build a neural net or build some model to do bone suppression. And it turned out that actually was pretty easy. I mean, building the model to do it wasn't that hard. Now, over the years, we've made many improvements to the actual suppression, so it's very good in terms of suppressing bones across, all variety of patients and all that. But what I found pretty quickly was that, I had this model, it had this application to do bone suppression, but when I moved it to different devices, it didn't work very well, right? So it would degrade, and so that was a problem. So I had to figure that out. So that was sort of necessity is the mother of invention. That was sort of true here. So I developed a technique that effectively takes any chest X-ray in and produces a new chest X-ray, if you will, that in essence factors out the effects of acquisition. And so what happened as a result, the model that I had built was able to work across different devices. And so that's that the essence of that algorithm is something we still use today. So all of our sort of X-ray based applications and similar techniques and technologies used in our CT platform. So what it means is Riverain stuff is plug and play. So when our applications are used across the globe, they get used when new sensors. So something plugs in and it should just work. So that definitely was a sort of key moment, sort of working on this problem of, again, what would be called domain adaptation nowadays.
So say we're explaining bone suppression to maybe a clinician who doesn't have a background in AI or
right.
A newsletter editor. How would we explain it? What's the benefit?
There's a device, dual energy subtraction. So it exploits the fact that at different X-ray energies, certain tissue types absorb X-rays differentially. So, for example, calcium and soft tissue. So by for example, by capturing the image at two different energies, you can sort of manipulate these resulting images to remove out sort of calcium. So this would be bony structures or like say benign calcified nodules. So that's old technology that's certainly they had prototypes back in the 90s, if not in the 80s. And conceptually, it may have been older than that. So the motivation there, in part, is if you remove the bony structures, say the clavicles and the ribs, you can see the underlying soft tissue. So subtle nodules, for example, are much they're clearly visible when you remove these. And we've lots of cases and users that use this application and can sort of testify to that. So that's the primary motivation. But the thing with dual energy is that it required effectively a special sensor, which means a special room. So, and it requires more radiation because you're basically imaging the patient twice. So more radiation, limited sort of utility in terms of availability. So a motivation for the software was clear, and indeed. There was some earlier work in maybe 2000. Somebody had looked to do an algorithmic approach to bone suppression. And I'm sorry, I don't remember the name, but at any rate, so there was a motivation there. So moving forward to realize this in software was really the challenge, right? And so, but even after taking care of acquisition, I said it wasn't out of the woods yet. So what I found along the way was that you want to remove bones, you don't want to remove abnormalities. And so this is what I found. So it's sort of like, okay, now you had another problem where you want to be able to remove bones but not abnormalities. So what I sort of realized was that I could, what I hoped was I could synthesize, artificial lesions, insert those, and then train the neural net just off of the synthetic data. And after some work and tinkering and so forth, it worked out well. But our ClearRead Bone Suppress is the product name. I don't know this for sure, but I suspect it's the first approval that was built entirely off synthetic disease.
Wow.
And so again, it was sort of necessity. So if you don't, this was sort of very modern concept, but basically the problem was I have a neural net, I want to train it. It's sensitive to devices, so you had to solve that. You sort of need a lot more data, a lot more variation. but that variation in data is very hard to collect, right? So anyway, that worked out well, and so those sort of became a couple cornerstones in terms of how we approach problems in general now, right? So we certainly take care of device variation, and to the extent possible or where it makes sense, we'll make heavy use of simulation. So that there were some other things along the way in X-ray space, but I think fast forward some number of years, we worked in CT, and this is what led to clear-read CT. This is vessel suppression and lung nodules. That's a bigger story there as well.
Cool. Yeah, and obviously the clear-read CT is not to be understated, right? That's and maybe we can get to that in a little bit. Curious. So you mentioned earlier essentially your kind of foray into lung CAD, and then that you might have gotten some publications, but it wouldn't have worked out to anything. And kind of I see that a lot. Plenty of publications that feel like a breakthrough, and then the public kind of painting AI with a wide brush and just saying like, where are all these breakthroughs?
Yeah, so right.
For you, it's like, where are all these breakthroughs?
Yeah. Well, the thing you always have to sort of remember is like, there's people's motivation. So I can probably guess a handful of things you're referring to, right? So, some big news splash, AI finds pneumonia better than doctors. Is it going to replace the radiologist or something? 4 years later, 5 years later, it still has not, and in fact isn't even used. So what happened, right? So I think I have maybe multiple sort of things that could be going on. One, if I think for sure, is this problem of acquisition. So it's the problem. Sometimes it's referred to as patient population, right? But if you go 50 miles north and your thing doesn't work, that's really not the patient population, right? So convolutional neural nets, which is sort of the workhorse right now, and deep learning AI is really, I think, sensitive to some of these effects. And so it depends on the problem, but you can train a model, get really good performance on test data. And so long as that test data came from the same source, then everything can seem good, and that you get excited and you make some announcements, and lo and behold, it turns out not to be true. I think that's one part of the story. Maybe a more subtle part of the story is I think ultimately how deep learning really works, which is in neural nets in general. And again, not a new idea here, but they're very good at mastering the typical example at the expense of, say, maybe the less frequent example. This is the so-called long tail, where you have this sort of spread of atypical examples because of their infrequency don't really affect the weights of the model. And so that in itself is one of the reasons why neural nets can be hard to train. But the real problem too is that if I go to sample the world to get a validation set, it's very, very easy to get a validation set by chance that suggests very good performance. So in other words, if I sampled the world for 10,000 lung nodules, right, in CT, well, like 9,000 of them are going to be about a centimeter in solid nodules, right? So they're basically the same nodule. So it doesn't really help you to kind of just, one, build models off that type of data, but two, certainly to assess performance. Machine learning is hard. I mean, it's particularly in medicine, right? It's not like the cat image where this thing sitting right in the middle of the image and you just have to sort of say cat. You have to look across a wide range of complex imagery to find these objects that can be obscured and again, devices, noise, and so forth. So it's a hard problem. I think things have gotten a lot better. I think the hype seems to have died down somewhat. I think nothing like trying to actually take what you built and use it blindly to humble you, and maybe that's part of why things have quieted down a bit. I don't know, but I think there's real use cases here, right? So I think certainly many more than just Riverain. So I think there's been a handful of companies that I'm aware of for sure that have built real no kidding applications that are being used daily by clinicians. So I wouldn't want people to have the wrong impression that it's all hype but I do think you mentioned something that I think is really important, which is these sort of suitcase terms, AI or CAD. I mean, these are just acronyms, right? And it's not like there's just one AI that if it works or it doesn't. I mean, there's quite a bit of engineering, and I think that's also part of the story, right? That to get these things to work really reliably, you have to do a lot of engineering. You can't just be a grad student who gets some data set from university's hospital and builds a model and think you're gonna. It's just not that easy. So that's, I think, probably what's going on there.
That makes sense. And thanks. I know that was a little bit of a curveball, but you handled it well. I'm curious. So you talked a little bit about kind of generalization and performance from one facility to the next, even if they're 50 miles away. And I've had conversations with ClearRead CT users, at Duke and in Austria. Yeah. What were the things, without kind of revealing your secret sauce, what are the things that you did to ensure kind of this ClearRead CT's ability to generalize?
Yeah, well, I mean, it kind of goes back. I mean, Riverain's been, open about how we build our technology, right? I mean, we don't like put source code on the internet or publish it in detail, but part of our motivation to explain what we do and effectively why we do it and how we do it is to build trust with clinicians. This is something we've been doing for years. So to answer your question, I mean, the thing to think about with AI, I mean, there really are like two principal sources of variation that you have to be aware of. On the one hand, there's variation that is not predictive, things that you don't want the model to key off of. So like, for example, you may be familiar with this experiment somebody did where they showed that the model used the view tag and a chest X-ray to classify pneumonia. So it's like it sort of underscores the point, right? And more recently, unfortunately, even models that could predict race with high accuracy. And so we can talk about that one later if you like. But at any rate, so what we do is we try to factor out variation that is not predictive. So this is acquisition. This can be the body composition. So things that we just don't want the model to have access to. So and this is this is not something we just started doing recently. This is something we've been doing for many years because it's just good machine learning. On the other end, there's variation that you really need a model. So this goes into simulation. So when we built ClearRead CT, when we started working on it, sort of looking at the space inside this lung nodules, for example, there were, commercial applications for solid nodules. There was not for the entire spectrum. You look into that and say, well, why is that the case? Well, the so-called non-solid nodules were much more difficult, rarer compared to solid nodules. So a number of reasons why, I suspect. But at any rate, so to really tackle that problem well, we made heavy use of simulation. So if you look at ClearRead CT and in particular vessel suppression, you'll see it do these really super clever things, right? It's sort of amazing, but in part because it's because of simulation, it's so well sampled, it can sort of do these magical things that probably surprise many people. But that's how it works. And one of the benefits of doing it that way, one of the big concerns with AI right now is validation. Like, how do you know this works, right? And so, one concern would be that if we have all this, say, data available, and if most of that data gets used to train the models, there's very little data left to validate, and that's a real problem. And I think it also goes back to your question about where do breakthroughs go, right? Well, if the validation is weak, then that's certainly part of the story, right? So something like where you train an AI on 70,000 images, and then you validate on 1,000, right? Mm-hmm. So it's probably the case that needing 7 municipalities to build a model is probably a bug, not a feature. Not something you would necessarily want to brag about. And then using like a high school to test it, sort of, that doesn't seem like in proportion, right? So in medicine, it's the opposite, right? So in medicine, they'll have like a small hypothesis based off a couple of patients, then they test it on a huge patient population. So AI is sort of kind of backwards in terms of relative what you have in medicine. So to the extent that you can preserve data to validate your models, which is what we're doing when we use simulation to build a model, you have a lot more confidence. You can have a stronger case to present to users, and then ultimately you sleep better at night because when it's out there being used that it's you've done what you could to make sure that it behaves in a way that you expect.
Got it. Awesome. Okay, so now we're gonna kind of look into the future, right?
Okay,
which is
sure.
Hard to get right, but fun to talk about.
Right.
So when you think about the future for Imaging AI and and Riverain within it, what are the things that you're seeing?
I mean, I think there'll be a lot more of the same. So, and by that I mean, as AI proper, it begins to sort of add more and more sort of techniques to how to make better comm nets, for example, or better deep learning models to be more general, things like attention and so forth. Like these improvements will sort of immediately be absorbed. So what I can see for sure that AI and radiology and I think medicine in general is going to get even better. And better means multiple things like sample efficiency. For example, like I just made reference to needing a lot of data to train. That's definitely going to be something that improves quite a bit using things like these so-called attention mechanisms where you don't just analyze the whole image, but rather you focus on key areas to kind of do the classification. Unsupervised learning, where or self-supervision, where you're trying to sort of find the right type of measurements or features to characterize an image without the strong supervision that we have today. And I think that's going to prove more and more useful. Particularly given like what you may have seen with, in fact, I know you've seen it because I saw it in the Wire, Luke's paper on race prediction. I think that is definitely something that is going to become a bigger issue. Like, these models, like, how they're built really matters, right? That it's not just about your performance curve. It's, where did that come from? How did you derive that? And so, yeah, I think those type of topics, transparency and explainability, perhaps those are going to become more and more important. So I definitely see that direction. And Riverain is working in that regard. I think in fact we have been. I think one of the reasons why we produce things like vessel suppression versus sort of hiding it under the hood and just having really high performance is, well, one, it provides an interface to the clinician that they understand. It's very intuitive, and so, but it also shows them sort of how the model sees the entirety of the image. It doesn't just put a box on the image, right? So so I think more collectively it's sort of, if we're going to, I think what I hope to see is that AI is going to be used to do more than just put boxes and on rectangles on lesions and generate heat maps, right? So I'm imagining a future where more information that makes the reading easier, right? Not necessarily harder or more time consuming. So I think that'll become the prevailing theme, right? So certainly where we're heading, and I think it's going to be well received by the end user.
Okay, excellent. I feel like if we got into the whole AI predicting race and images thing, we would just talk for another 35 minutes. So,
oh yeah, that's a big topic. Yeah, maybe have Luke on for that one. I think that would be a great topic to have. I mean, why it's significant doesn't seem to be, I think, appreciated. Just based off the Twitterverse, right? I see Luke out there posting, and people, it's really an important result, and I think it definitely has implications on how certain groups or certain AIs are being built with regard to, say, using weak supervision, where they just say there's a nodule in the image or there's a pneumothorax. That is very problematic. So I think this should definitely cause people pause, this result. So.
Right. And it's good that we have people like you and Dr. Luke working on that and really trying to, not just kind of create a hacker tool, but, understand the way all this stuff works so you can, solve some real problems. And that one seems to be a systemic in addition to technology problem. This is a lot of information, really good stuff. I'm curious if there's anything that you feel like the world and the viewers out there should understand about imaging AI or what you're working on in Riverain, some kind of really important takeaways that maybe we didn't have a chance to address, and then we'll say goodbye for now.
Okay. Well, Riverain's marching along, producing a lot more applications. So from our sort of corner of the world, we're looking to sort of create more offerings in our platform. Look to build sort of technology that I think is above and beyond sort of putting boxes on the image. So I think working backwards from the clinical point of view. What do they really need? I think the thing to understand more than anything else is that the shift of focus, about what we would talk about, right? There was a lot of talk about replacing radiologists, but I think that's gone, but sometimes it creeps its ugly head up again, and it's sort of a distraction. So, I mean, the reality is we need more radiologists, right? And I think what will be found is that the big problem to be solved is burnout. That and having AI that maybe only marks 1 in every 100 image. I mean, that sort of has a very high specificity. That sounds, and that's kind of important. But what it really means is that for most cases, it's not really adding any value. So they still have to read it like it's, circa 1999. So you want to, I think the big picture here in AI and radiology is to really kind of think through, what can it do to really help the end users to the full extent, and not just in those moments where there's a pathology.
Awesome, Jason. Thank you very much.
My pleasure.
Congratulations on being the fan of the best football team in the world and America.
Yeah.
And congrats on all your great
universe.
work in the not bad. All right, I'll catch you soon, buddy.
All right, take care now.
Bye-bye.
Bye-bye.